All right, how's it going, folks? The other day we talked about relative dating, getting a comparison ages of rocks, right, to figure out Earth's history. Today we're going to chat about how they try to connect more of an exact number to that. They call it absolute dating. And there's a really cool method they use called radiometric dating. It has to do with the instability of atoms, right? They go through half-lives as they're breaking down at a predictable rate. So really cool stuff. And that's how, of course, they dated the dinosaurs. These are trilobites, ammonites, you name it. And you can use different materials to do that type of dating. So I want to start out with a little clip from the movie The Mummy. Maybe you've seen it. Listen carefully to what they say, aside from the comedic dialogue.
About dead guys?
Look, the sacred spells have been chiseled off. This man must have been condemned not only in this life, but in the next.
Right. Yeah, I'm over. Cheers. Alright. See you inside, shall we?
Oh, I hate it when these things do that.
Is he supposed to look like that?
Oh, I've never seen a mummy look like this before. He's still...
Juicy.
Yes. He must be more than 3,000 years old, and well, it looks as if he's still decomposing.
Yeah, look at that. What do you make of this?
Oh, God, be smart for me. Fingernails. This man was buried alive. And he left a message. Death is only the beginning.
All right, how do we define absolute age? There it is, the actual age of an object in years. And the method, of course, is called radioactive or radiometric dating. All right, starts out with the atom. You've all heard of subatomic particles, right? Protons, neutrons, electrons. Well, some atoms are stable and they'll stay that way for all eternity. But others are not happy. They're not stable and they're giving off something and they're breaking down until they become stable. Sometimes they give off protons, sometimes they give off electrons. It all depends on the type of atom it is, and that'll make them either positively charged or negatively charged and ultimately turn into another atom, and we call that radioactive decay. Okay, that's a big piece of how this dating is done here. So, how does it become unstable? Well, stable non-radioactive atoms are balanced, nothing's being given off, nothing's being taken in. But if it's unstable, it's because there's a different number going on there, and the atom either wants to get rid of something or get something to make it more stable. And in doing so, it gives off radiation and also becomes a different material, which is pretty wild. Okay, we call it an isotope, right? Atoms of the same element that have the same number of protons but a different number of neutrons, and as a result, they are giving off energy we call radiation. Okay, so how does radioactive decay occur? Well, carbon-14, for example, is an unstable isotope of carbon, and as it's breaking down, it turns into nitrogen-14, and it does so at a predictable rate. So when it's at certain points, we call them half-lives, we know how old it is. So for example, if you go to your reference table, and I'll show you the chart in a second here, if you go to your reference tables, carbon-14 takes about 5,700 years to go through one half-life. So if you find a fossil where the amount of carbon-14 has been broken down halfway, you say, it's got to be 5,700 years old because that's its half-life. And then you could keep adding those up depending upon the number of half-lives. Or if it's a different element you're looking into, you can look up its half-life and do that same process. Okay? So the parent element here, unstable, it will decay. And it will turn into a stable, what's called daughter product over time. And you can have some fun with your folks on that. You could say, whoa, in science today we learned that the parents are unstable, but the children or the daughter is stable. I wouldn't discuss that at dinner, but hey, it's up to you. Okay? Anyways, an unstable radioactive parent decays or breaks down at a predictable rate, and it will turn into a daughter product. Okay? Kind of looks like this mathematically. So let's say you have 100% parent. Let's call it carbon-14. Over time, it will decay, and when it hits that 50% mark, we say it's hit its first half-life. All right? And now, if you take half of a half, you get a quarter. When it hits this point, it's at its second half-life. Well, a half of a quarter, then drop it down, you get your eighth there, and it keeps going, and each of these marks is a new half-life. So this has gone through 1, 2, 3, 4 half-lives at that point. Now, it'll never, ever fully disappear, right? It'll never fully become 100% daughter product. However, it'll become so much of its daughter that it'll become immeasurable at some point. All right? 15 or 20 half-lives into the future, there's so little parent left that the amount is insignificant. You can't measure it anymore. Okay? If that happens, then you got to switch to a different element that has a slower half-life so that you can date older things without running into the scenario where you run out of the original parent product. Okay? Or parent material, should I say. So there's your half-life definition, right? The time required for half of the radioactive element to decay into its new element, its daughter product. Okay? This chart works for any element, by the way. Notice I didn't put any names on here, any years. So you could apply it to anyone, go to your reference tables, and you could use this same chart. You would just put a different number of years for each half-life and a different parent or daughter element into the diagrams. Okay? Okay. Here's the chart I'm talking about. So carbon-14 turns into nitrogen-14. It takes 5,700 years to go through its first half-life. And what I mean is, from here to here, for carbon, it would take 5,700 years. Okay? Now, if it's another 2 half-lives, then you would simply go 5,700 plus another 5,700, add that up, and you get 11,400. If it's another half-life, add another 5,700, and you would get 17,100, and you just keep going. Okay? All right. Notice other elements have different half-lives. Well, 5.7 times 10 to the third, that's 5,700. But look at this one. 1.3 times 10 to the ninth. Okay? That's 1.3 billion years. That's a much slower half-life. It takes a lot longer for potassium to break down than it does carbon. And that's very helpful because there are many things on Earth a heck of a lot older than 5,700 years. Like the dinosaurs, for example, went extinct 65 million years ago. Well, you can't use carbon to date a dinosaur, right? By the time you got back to 65 million years, the half-lives of carbon would be all used up in a sense. You really couldn't measure it anymore. So you have to switch to a different element that you would find in that creature, such as potassium, or believe it or not, uranium is also found in living things. Okay? Rubidium would be used to date like very old meteors. So here it is. This one is used to date relatively younger organic remains. This would be good for dating a lot of old rocks because remember, granite has a lot of potassium in it. Okay? This, of course, also for old rocks or living things that have it inside of it. Rubidium they tend to use for dating even older, like meteor type of samples. An element's half-life, its rate is not affected by temperature, pressure, or any other factors. The only thing that affects it is time, unless the sample melts, right? If you melt the sample down, then you start the clock over, and you go back to 100% parent. Other than that, doesn't matter if you heat it up, squeeze it, put acid on it, it's still going to decay at that same rate, which makes it a very reliable dating tool. Okay? So make sure you get that in your notes there. All right. At the end of one half-life, a sample contains equal amounts of parent versus daughter. In each succeeding half-life, half of that remaining atoms decay and it becomes greater daughter, right? Mostly daughter until the end. It's pretty much all daughter product. Okay, here's a funny little joke for you there. And careful with these insurance salesmen, they get you. So here you go. Further, this policy halves your benefits until there's nothing left, at which point it won't matter since you'll be dead. How does that sound? Not half bad. So basically, he's selling a life insurance policy that'll be worth nothing when the person passes away, probably. Okay. So there's a summary activity there. I need you guys to try to plot that out and fill in the chart there. And of course, hit pause here a second. All right. And then when you do, you should come up with an exponential decay type of graph. Okay. Then you have some extra summary questions dealing with different type of visuals on how to get half-lives. Okay? All right. I'll meet you back in the meet.